Hello everyone, welcome to my YouTube channel, this side Priya Bhatia. And in this specific video, I will be discussing about logarithmic. Yes, you heard it right. Logarithmic plays a very important role in data structure and algorithms. And I have curated a complete playlist for DSA using Python on my channel. But one thing which I have realized that people don't appreciate the power of log. When we shifted from linear search to binary search, we have observed that somehow the complexity get reduced from big O of n to big O of log n. We have seen that people appreciate the time complexity of logarithmic because it is far smaller as comparable to big O of n. But what is the reason behind that? What is the internal intuition behind that? Why people usually appreciate a code which is of logarithmic time complexity as comparable to linear one, and that code only will be useful in a real world applications as well, right? So today in this particular video, let's dedicate this session to understand that power of log, specifically in data structure and algorithms, so that in future if you will see this keyword, and if you will encounter any code where you are facing a trouble that okay, can I convert that code into logarithmic, what power actually you are trying to give to this, to that specific code, let's try to understand and deep dive into that part. So without wasting any time, let's get started. So whenever we are talking about log base b x, let's suppose, basically it conveys that this particular logarithmic part is equal to, let's suppose, y, if and only if and only if you are trying to convey that x is equal to b to the power y. That is the mathematical idea behind log. Okay, now just let me write down in a better manner. So this is the intuition. Usually we represent in mathematics terms via this I double f. So in other words, you are trying to interpret this thing when you are saying log base bx is equals to y. For example, when we're talking about specifically in DSA, and whenever we are using the log term, for example, log of, let's say I'm saying 1, right? So by default in DSA, we assume that the base is 2. By default, we assume that the base of log is 2. And that is why, if you will be able to observe, we always say log of 1 is 0. Why is that so? Because just try to understand this. Just try to do, if you will assume the default value as 2, so what will happen? This 2 ki power 0, this 2 ki power 0, can I say it will be equal to 1 only? So just try to compare the above equation with this one, because I have seen so many people are confused in this logarithmic part. And today, I think after watching this session till the very end, you will be able to get a better clarity of this concept, right? So please make sure you will be very attentive and you will be able to understand this in a lot more detail. And please make sure you will hit like button and subscribe to my channel as well, because it usually takes a lot of time to curate this kind of a content, right? So now let's come back. So here you can see, right, what I have done is, this is x in my standard equation and this is b, right? So what we have mentioned, x is equals to b to the power y. So 1 is equals to 2 ki power, y is here 0. So that is why, that is the main reason that y log of 1, which is by default base as 2, is equals to 0. Similarly, if let's say, if I'll ask you what is the value of log of 4, so by default, if the base is 2, so you are saying the answer is 2. Why is that so? Because internally what is happening? Internally what is happening is, the internal intuition is, you are somehow saying 2 ki power 2 is equals to 4. Now I hope it is clear to everyone. Now the question is that what impacts it does have. For example, if we have written some code, we have a linear search, right? I hope you all know we have a linear search. So in the searching algorithm space, you must have seen that we have two separate techniques of searching. One is linear search, another one is binary search. But if you will be able to observe, binary search is very widely used searching algorithm, and people usually prefer to go for binary search if we have a sorted array altogether. The main reason is that in linear search, we have a complexity of big O of n. But in binary search, we have a complexity of big O of log of n. Again, whenever I am saying log of n, default, it is by default 2 only. So what actually happens and what is the significant difference? Is that a bigger difference? Is it a smaller one? Let's try to understand it visually today, right? Graphically, we will try to understand this thing. What is happening? Okay, we have seen the intuition, right? We have seen the intuition. If let's say you are working with the exact number, you're working with the exact number means you're working with 0 value, you're working with 4 value, and so on. So what is happening is 2 ki power 3 is something which is equals to 8. Can you observe that when you are increasing the exact value of n, this n number increases exponentially. But here, if you just increase by one number, right, your value increases abruptly. 16 is coming up, right? Just by increase of a single number here. Just by increase of a single number here, your value significantly increases from 8 to 16. Same thing will happen further. If I will say 4 plus 1, it will be 32. Again, if you will be able to observe, my value abruptly increases from 16 to 32, right? That is the significant difference which you should be able to observe. What is happening in log is, when you are saying log of n base 2, so what is happening, if you will be able to observe it, if it is equals to y, or log of, you are saying x base b is equals to y. So what you are saying, in other words, you are saying that the value of x is nothing but is equals to b to the power y. This change is very small. In other words, if let's say you have a big array, and I will just give you one simple example. Let's say you are saying that I will be having an array of size 8, 0, 1, 2, 3, 4, 5, 6, 7, right? And you are trying to split this data into multiple components by 2, by 2, by 2, right? So how much cuts are required? How many cuts are required? So you will say, firstly, you have cut down into 2 components, equal splits. This is gone. Again, you have 4 components, you have further split it down. This is gone. Again, you have 2 components, you have split it down. This is gone. Now you're left with a single element. It means when you have 8 elements, only 3 cuts are required. And what do you think? This is nothing but log of 8 base 2. Only 3 cuts are required. Now in terms of n, if you will just double this size from 0 to 16, 0 to 15, means if you will take this number of elements as 16, what you will be able to observe here is, in terms of number, it is increasing almost double, but in terms of number of cuts, only 4 cuts will be required, which is nothing but log of 16 base 2. So the value, as the value of n increases, what you are observing is, as the value of n increases, what you are observing is log of n by default base 2 is also increasing. It's not that it is not increasing, right? For example, initially when n is 8, only 3 cuts were required. When the value of n, we have doubled almost, 4 cuts are required. So it's not that log of n base 2 have not increased. It's also increased. But log of n base 2 is also increases, but only by, you can say, tiny amount. So the impact is not that much bigger. So when you are saying linear search is having big O of n complexity, so what is happening? As your value of n increases, search space will be increasing. It will take more time. But on the other hand, when you're saying log of n base 2 is my complexity, even though your value of n become doubles, the log of n value will become very, very small increase. just by one number. That is why when I always say in a binary search, like the way it works, that we are somehow splitting our search space into half, 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 people don't understand that how is this happening. In other words, the intuition of logarithmic is dividing the complete space into by 2, by 2, by 2 until we reach to a single element. Now, I hope you will be able to understand this point. Why is that so? Because when you're trying to increase your value of n, I'll just try to now showcase this example with the help of this Desmos tool. Here you can see I have one value which is log of base 2x. Can you see the graph? Red line indicates the graph of this. If you will be able to observe in this graph, this value is increasing initially, and after that, increase is very small. It's almost stagnant. So if you can see, the value of, as the value of n increases, as the value of n we are increasing, it is from 50 to 100 to 150 to 200. Can you see the change in the value of y? It is almost stagnant. It is almost similar. That is why log of n is a good time complexity. Because the time required to execute a code, even if the value of n is keep on increasing, is less. And that is what we want in our, optimal code part, right? But on the other hand, when you're saying 2 ki power x, what is happening? As you're increasing your value of n, your value of, you can say y, or the value of result will exponentially increasing. So in the logarithmic, what is happening is your graph looks something like this. It's like something increasing and then it's very stagnant like that. But on the other hand, if you're having a n time complexity, so you are saying that somehow as the value of n increases, my value of time is also increasing. But what we want is that even though our value of n is very, very huge, the time required to execute the code should be very optimal, very less. And that is why logarithmic plays a very, very crucial role in case of DSA, right? That is why we always look for a result which is having a logarithmic time complexity if possible. And that is the main reason, that is the main maths behind that. I hope it is clear to everyone. With this, I will see you all in the upcoming video where we will discuss another interesting, important, concepts related to data science, DSA, AI. Bye-bye everyone, and I'll see you all very soon.